Thank you, Vincent. As I was just introduced, I'm Kunal. I'm a postdoctoral researcher at Georgia Tech, and previously I've done my research in TU Eindhoven in the group of Rene Janssen. So most of my work, I've just been here for a couple of months almost. So what I'll show today has to do more with my PhD. And I adapted the title of the talk a little bit, keeping same theme, but just to be a bit more specific and to kind of focus on what I'm actually going to talk about. And the title and the focus of the talk would be to mix halide perovskite-based multijunction photovoltaics. So tandems and maybe a small segue into triple junctions, perhaps. And I decided as a kind of a subtitle to put it as from a marriage of convenience to one of equals, because, and I'll come to that in a bit about why that was the motivation. So this is the team that worked on this project, and we are spread across the Netherlands, across 3 institutes, TU Delft, TU Eindhoven, and TNOS Alliance. And it's done in this project was done under the auspices of the JSP3 project, so Joint Solar Program funded by the NWO, and a couple of other programs under the NWO. And so it's a truly collaborative project that we did with my group listed here, the group from TU Delft led by Olindo, PMP from TU Eindhoven, where they are specialists in ALD by Adriana Creatore, and TNOS Alliance, some of these people you have seen in other works in tandem solar cells. So so the outline of the talk today is kind of more or less listed out here. So I'll first discuss basic principles and what you need to look at in terms of design considerations when you're thinking about working on a monolithic multi-junction device. So tandem triple, the same principles apply more or less. And then I'll first start off with the experimental work on charge transport interfaces for the perovskite subcells. So the whole transport layer, electron transport layer, and then interfacial passivation and things like that. Then I'll jump into perovskite-based multi-junction solar cells with a silicon bottom cell, and then followed by perovskite tandems, and then finally some take-home messages and some design challenges and materials challenges. So yeah, just to motivate where we are and why we need tandems, I think most of us know already, but just in case, just to brush up the fundamentals. So if you look at the single junction solar cell, so for example, there's a schematic, and you have light of different wavelengths coming in, what is a typical loss process? There are 2. Is the first one is thermalization loss, wherein you're hitting it with light which has an energy higher than the optical band gap, and therefore you excite your carriers to a higher energy, and then they need to come back to the the valence band and the conduction band switch. So they need to come back to the conduction band minimum, and this energetic loss is your primary loss, and that's your thermalization loss, right? And the next one is a transmission loss, wherein you are exciting this light, but with light which is below the band gap, so it actually isn't exciting, it's getting transmitted through, right? So you're losing carriers in that way. So these 2 are the loss mechanisms that kind of limit single junction devices in pretty much every platform that you can think of. You can make your to reduce the transmission loss, you can minimize the optical band gap as much as you want, but then this will kick in, and then vice versa. So the way to overcome that is to make a tandem or a triple junction device where you can actually go further with the number of layers. And where all you're doing is splitting the incident light spectrum, right? So you're using a narrow bandgap absorber to get the carriers, to get the light from the narrow bandgap, so from the low energy side, and you're using a wide bandgap absorber to get high energy light. And if you do it right, and if you balance charge as well, then you get a good working device. The same applies. You can basically go a step further and make a triple junction device where you're actually tuning the device according to more splitting the spectrum into more sets. right? And all you're doing, therefore, in terms of, you want to think of it not as optics, but as devices, all you're doing is you're adding the voltages up of each of these cells, and you're dividing the current. So your EQV spectrum is getting divided into as many parts as the number of junctions. So in the field of perovskite-based multijunctions is not very old, but it's not very new either. We're kind of starting off here around 2015, and so I've listed out the key developments in the field in the last like 10 years, almost 8 years, something like that. And split across the perovskite-silicon platforms and the perovskite-perovskite platform. So, for example, as when the single junction space, the most efficient solar cells at that point were still the narrow bandgap, the NIP devices. But then quite soon we realized that the PIN polarity is better in terms of optics, just because you lose a lot of parasitic absorption that you would otherwise have in the NIP devices. And then people have tried to work on textured cells, and then to reduce the optical losses further by self-assembled monolayer hole transport layers, and then of course light management. There is still one NIP solar cell which was reported a few years ago, which is very, very good. So there is still possibility in that space, but it's not the materials space is not as large as in the PIN case. The same applies to perovskite tandems. The big development was the coming of these let-in narrow bandgap perovskites, which allowed bandgap tuning, which started somewhere here. And then these devices, because they are thin film, you can use them as flexible devices. So that comes in here with pretty good efficiency. So the climb in perovskite tandems has been much more significant, much more exciting than the case of perovskite-silicon tandems. So in terms of what you need to think of with respect to how to design a tandem in each of these platforms. So this was the schematic that I showed, but actually if you need to make a monolithic device, you need to introduce something called an interconnection layer, right? And that is where the charges, so the electrons or the holes, depending on the polarity, from the narrow bandgap cell and the opposite charge from the wide bandgap cell kind of recombine, and that maintains charge neutrality. And that gives you a good device, right? So you need a layer where you can collect carriers from both sides and where they can recombine quite efficiently. And so that is one consideration, and I'll come to experimental parts of that in both the platforms later. And in terms of how to construct such a device, for instance, for a perovskite-silicon tandem, there's only one way to build it up, and that's that you start from the silicon cell and then you build up the perovskite, and that's primarily to do with processing considerations. That the temperature and what kind of harsh processes you use for a silicon cell, you cannot do it when you're doing it on top of the perovskite. So you need to do the perovskite at the end. In the case of perovskite tandems, you can go in either direction, and typically it's done where you have a wide bandgap solar cell, and then you go and deposit the narrow bandgap cell. So you go this way in the row from top to bottom. The other way is also possible, that you deposit a narrow bandgap solar cell and then deposit a wide bandgap solar cell. There are a few reports recently, especially on that kind of architecture. But the stability of the narrow bandgap solar cell to those kind of processes can be a bit of a restriction, but it's possible in principle and also in practice. So what you're looking for is, in the absorber, you're looking for a high radiative yield, so preferably a defect-free layer or defect-poor layer. Perovskites are never defect-free. You're looking at a layer which is thick, so that you can get a very high EQE, and that means that because these layers are series connected, you need the current by each of these layers to be the same or close to each other, in order to not lose any JSC. Otherwise, the subcell that amount of current determines JSC. So ideally, you want them to be as thick as you can make them, and that results in a high JSC in both of them. You want them to be stable, and that's not just from the performance side, but also from the processing side, because you don't want the deposition of one subcell to affect the other. right? So there are a few additional steps that go into it, and therefore you want your materials to be as robust as they can be. Transport layers, you need better energetic alignment. That applies to single junctions as well. That's nothing new. But one thing is that, especially with tandems, that you need your transport layers to be as transparent as you can make them, because you're depending on the transmission of these transport layers for the performance of the second cell, and therefore the lower the parasitic absorption can get, the better. The interconnection layer that I just mentioned, in the case of a perovskite tandem, it also needs to act as a solvent barrier, because as you can imagine, if you're doing both the cells with solution processing, the deposition of the second cell will, the solvents for that will affect the first cell. So this layer in between needs to be quite dense and therefore protect the underlying device. This interconnection also needs to have high conductivity so that it can kind of collect carriers efficiently. And again, as the same as the transport layer, it needs to be transparent to minimize any kind of parasitic losses. Okay, so yeah, coming back to the motivation. So this review came out in 2017, I think, around the time when I was starting my PhD, and it was a very good review to get started with as a first-year PhD student. And the title was quite interesting, because that is Silicon Tandem Cells, a marriage of convenience or a true love story. Because at that time, these devices had only reached 25%, slightly lower perhaps, and so it was a question that, okay, how far can these devices get? So it was quite an interesting and striking title that I got. And this was from EPFL, and one of the statements on this review was, it's not yet possible to give a precise prediction about when the first 30% perovskite-silicon tandem cell will be demonstrated. And surprise, surprise, give it a few years, and EPFL itself demonstrated 30% above, not just one, but two perovskite-silicon tandem cells. So in some ways, they predicted or questioned their own outcome. But the journey from here to here, I think, is an interesting topic, because, and that's kind of where my talk comes in, that in the beginning, you would think that, okay, silicon was established technology, so it was, let's say, strategically good to combine perovskite with silicon in order to be able to boost the performance. But are they really compatible? And I think going from here to these new records, that is purely based on the idea that indeed you need to kind of have the subcells work with each other, right? So there needs to be a very amicable partnership between the two cells. So you're not using you're using the benefits of both subcells while kind of processing them such that they are kind of compatible. And that's what my PhD was mostly about, as to how to improve this partnership between the two subcells in a monolithic tandem. So yeah, I would then discuss transport interfaces in these perovskite subcells, and specifically I would focus on the wide bandgap device. And the first thing, and this has been on the subject of a talk from a previous speaker at this forum, and the first thing that we looked at in these devices was the self-assembled monolayers, and that's to do with the hole transporting contact. So this is the general device architecture, and these are the molecules that we looked at. PTA was standard at that time, and these molecules were starting to come up. So these three were commercially available, and these two were synthesized in-house. And the first thing we looked at was the energetic alignment. So you can look at the ohmo levels of these materials here, and this is the kind of the band diagram of the 1.69 eV perovskite, which is suitable for silicon tandems, and the other one, 1.80 eV, which is suitable for perovskite tandems. And you can already see that these three, for example, align much better than the other ones, right? $2, $3, and $4. And we attempted to work with these materials, but $4 was difficult to dissolve, so it didn't really give us very good cells. And $3, the yield was a bit lower, but the performance was comparable. But because $2 had the benefit of both the yield and the performance, I decided to go with it. And if you compare $2 with PTA, and that you can see here, we take the product of the VOC and the fill factor, which basically translates to and efficiency in the rate of charge collection at that interface, and also the energetic alignment, right? Which basically bumps up your voltage. And you can see that across different band gaps. So this one is for tandems. This can also be used for tandems if you can get the optics right. But across all band gaps, you get a better product of the VOC and the fill factor when you use 2-pux compared to when you use PTA. So it was quite evident, and that's also been seen by other labs, that this material is quite robust and can be used across a bunch of different compositions. The next thing we looked at was the interface between the perovskite and the electron transport layer, so the perovskite and the C60. And the one thing that struck us was that if you take a perovskite with a certain band gap, let's say 1.63 eV, and then you widen the band gap to 1.80 eV, what you see is that the voltage, which is this dark part, keeps on going up as it should, but it doesn't go up by as much as it should, right? And that's because the VOC loss compared to the DL balance limit also keeps on rising. So that's here, the loss, sorry, this should be loss, as a function of the band gap that keeps on rising. So that is a strong limitation to the performance of these tandem devices. And what we try to do is we looked at this interface specifically. So the interface between the perovskite and the C60 layer. And when you conduct an absolute photoluminescence spectroscopy experiment, and that basically translates to your PL quantum yield, which translates to your quasi-Fermi level splitting, which translates to your voltage. You can see that if you take the bare perovskite, so just the perovskite by itself on glass, you get a spectrum which looks like this. And the moment you evaporate a C60 layer on top of it, your emission intensity drops, and therefore the quantum yield also drops, right? And that yield implicitly means that the quasi-Fermi splitting has also dropped. Now, if you treat this interface with choline chloride, that's this molecule here, it's a quaternary ammonium salt. It's a very thin layer from a very low concentration. You'll see that here. You see that this drop in the emission intensity is no longer there, right? They kind of overlap. And therefore, you can say that, okay, the emission non-radiative loss that you would otherwise incur in this interface goes down significantly. And we optimized this concentration for the voltage, basically, and we found this kind of a sweet spot, let's say at 1 milligram per milliliter. You can go a bit further, but not too much, because the current also drops a little bit. So this is kind of the best that you can get. And when you look at this passivation across 3 different band gaps, so this is the quasi-Fermi level splitting loss calculated from this absolute photoluminescence spectrum. And the moment you passivate it, it drops significantly. And then this quasi-Fermi level splitting drop loss keeps on rising, as I showed here. But this the passivation keeps this loss to like 4 to 7 millivolts. That's quite spectacular, I think. And that eventually, if you put it in a device, that results in an increase in the VOC that you can see here. And that basically means that overall your device performance goes up, right? So now we have looked at this 2-pux interface and the C60 interface as well, and kind of optimize it to improve the VOC of these devices. The photostability is also affected. For example, this is a paper that we had previously published where we had looked at mixed halide perovskite solar cells and measured the defect photocurrent in these materials. So for example, this is the wide bandgap material for 33% bromide, so around 1.74 eV. And you can see that these undergo light-induced halide segregation. So this dark spectrum is of a pristine sample. And after shining light on it, you can see that this photocurrent contribution increases, and also this Urbach tail starts to shallow a little bit. So that's an indication of making iodine-rich phases in this material, which at the end start to affect the JSC of your devices because they act as kind of traps. And so we use this technique to characterize our now passivated material. So this is, for example, the control 1.69 eV, and this shaded area is the pristine device, and we shine light for 1 hour after that, and then you can see that this defect starts to go up. The material is stable in itself because it's not as high a bromine concentration, it is only 25%. But so therefore this Urbach tail change that we can see here a little bit doesn't even show up here, but this initial set in of these defects you can see because the solid line is basically much higher than the shaded one. If you contrast that with what we see with the choline chloride sample, so the shaded one is the pristine again, and this solid line is after light soaking for 16 hours, they basically overlap. Right? So there is no increase in the defect photocurrent as a result. And we attribute it to the choline chloride, but it's because we don't know what kind of defects are there. There is some theory on it, but it's always a bit hard to get the defect energy correct. So we don't exactly know what kind of defects are being passivated or to what extent are they being passivated, because again, we can only observe defects that contribute to the photocurrent, right? So if there are other defects that are being passivated, we wouldn't observe them as much. But it is true, and it's quite clear that this light-induced behavior changes significantly. So not just the voltage, but also the stability of the device changes. All right, then we started to integrate these devices into multijunctions, so tandems. And the first one we looked at was perovskite-silicon tandem solar cell. And so this is the general stack of the device. So it's silicon heterojunction solar cell, an ITO recombination junction, that's the interconnection, and then basically a PIN device, the two pucks, and the wide bandgap perovskite, choline chloride, C60. We replace the BCP with tin oxide, and you need that to protect the C60 from any damage during the sputter of this ITO layer. But what we saw was that it wasn't as straightforward to integrate, so just kind of build up, because when became critical was this interface between the ITO and the two pucks, right? Because the ITO that was being used in the single junctions was something that we buy commercially. So the surface is significantly different than what we can process in our own lab when we sputter it instead. And that we looked at with XPS. So you can look at the oxygen spectrum of from the XPS, and you can kind of deconvolute it into two parts. One is the contribution from the metal oxide, and the other contribution is from this hydroxyl groups on the surface. And you can see that this is the commercial ITO, the one that we use for single junction devices, that you have a significant contribution of these hydroxyl groups. And but the moment we use the sputtered ITO, this goes down, right? And that you can see here the ratio of the hydroxyl of the metal oxide that you can see here. And as a result, this 2-pux layer wouldn't bind as easily on top of this layer where the hydroxyl concentration is poor. So we added a layer of nickel oxide, processed the ALD, and that increases hydroxyl concentration quite a bit, that you can see here. And that led to a dramatic difference in the devices, because this is the IV curve of the tandem solar cell when we were not using the nickel oxide, and the VOC is basically the same as that of the silicon solar cell, and the JSC is similar to what you would expect out of a silicon solar cell being filtered optically by the perovskite solar cell. So it's as if the perovskite solar cell is not contributing anything to the device performance. But the moment you put the nickel oxide layer in between, it shoots up, right, and gets significantly closer to the sum of the VOCs of the perovskite and silicon solar cells. So that was very interesting for us, and that really made a big difference to how we kind of proceeded. And you can see the cross-sectional SEM of the tandem, and this is kind of what the tandem looks like. It's a square centimeter device. So this basically the integration is interface is enabled by this nickel oxide layer, which is quite thin, but it's very very important. And then once we got working devices, we did some light management, and we started with some optical simulations. So we generated kind of a simulated absorption spectrum based on experimentally determined optical constants. and that you can see here. So it's the same stack as before, and this is kind of what the absorptance of the different layers look like. So there's the perovskite contribution, this is the silicon contribution, this part is the overlap between the two, so basically this part. This is the parasitic absorption, because you are shining light through here, so you have parasitic absorption here, here, and a few other layers here. And this light gray part is the reflection loss, right? And if you kind of split up the parasitic absorption, you can quite clearly see that most of it is coming from this ITO layer. So this is kind of the equivalent of the JSC loss that you're having in your device. So most of it is coming from the ITO layer, some of it is coming from the C60 layer, and the rest of it is a bit less important to the parasitic absorption. The other bit is, of course, the reflection, because you're losing 8.1 milliamps from just reflection. So if you then use an anti-reflective coating, so magnesium fluoride in this case, so here, and reduce the C60 thickness to reduce the parasitic absorption, you start to get the reflection changes. So you almost half it. It's at 4.5 now. And that's because the interference is changing quite a bit. So you can see this this dip here, and that it goes down significantly. And what you're also changing is the C60 layer thickness, so the absorption there also goes down. And that allows us to make a tandem, which is at 25.1%. There's a bit of a voltage loss, but it's not significant compared to what's available in the literature. And most importantly, by these light management guided optimization, we can reach very good current matching between the two subcells. And so that basically means that we're not losing any current as heat, let's say. Yeah. And then we moved on to the next platform, so perovskite multijunctions. And there we first looked at this, just to jog your memory a little bit, this kind of a stack which I showed before. And we're building from the wide bandgap to the narrow bandgap. And this is what the cell looks like in reality. And the first thing we looked at was the this interconnection, right? And here it serves two purposes. Not just does this have an electrical role, but it also has a role with respect to the solvent barrier. So, for example, if you're depositing this cell on top of this, it should kind of protect it. So we try to simulate that by just taking this stack, so just this this cell, and spin coating water on it. And you can quite clearly see that depending on the thickness of this ALE oxide layer, you start to see these yellow blotches here, this yellowish line here, and then that's just degraded lead iodide. The moment you make this layer a bit thicker, so 45 nanometers going from 20, all these things don't appear anymore. It's much more cleaner, so there's no degradation as such. So that basically means that you can spin coat the P dot, and then later on the perovskite. So the P dot is part of some water, so therefore we tested it with water. Now you run into the same problem here, which is that there's a mismatch in the currents of the two subcells. So if you take a tandem device, so that's the schematic here, and then this is the single junction IV of the two cells, and this is the single junction IV of the tandem. And you see that the EQEs shows that there's a mismatch of about a milliamp, a bit more even, between the two cells. And that, in our case, it primarily stems from the fact that our narrow bandgap cell is quite thin, so it's 600 nanometers, which means that it doesn't absorb a lot in the first pass. And that's a bit different than what is elsewhere in the field, because if you look at this SEM image from this paper, which came out, I think, in 2022, the narrow bandgap cell is over a micron thick, 1200 nanometers even. And that really allows the EQE to go up significantly, right? So, but with our processing at that time, with this two-step process, we couldn't manage to do that. So we had to kind of find a different way to improve the current in our device. So again, we went to optical simulations, and this is again a simulated spectrum. So the wide bandgap, the narrow bandgap, the parasitic absorption, the reflection, and the overlap. And you start to see that in this case, the light is coming in through here, And the biggest parasitic absorption contribution is actually coming in from the ITO, so this layer. Then there is some contribution from the P dot layer, so that's this one, and from this gold layer, which is here, this one, and this here to improve the conductivity of this interface. But at the end, it also has some parasitic absorption. And then we try to optimize the stack by basically changing first of all this ITO layer and replacing it with IOH, and that's to reduce the free carrier absorption in the near infrared. And at the same time, we reduce this the thickness of this P dot layer from 50 to 20 nanometers, and you can clearly see that this parasitic absorption contribution goes down significantly. The next step to do would be to replace this gold layer with ITO. So this red part also goes down. And then finally, if you really want to get rid of all the parasitic absorption, you can remove the P dot and just use, let's say, a self-assembled monolayer methoxy 2-plus, for example. And that removes all the parasitic absorption that you can have, and that shows up on the simulator absorptions as well. That you can see that you start from here somewhere. The top cell remains more or less the same, but the narrow bandgap cell is what's most affected, right? You start from here somewhere like 60% in this range, and you could go make it all the way up to like 90%. And if you try to do that in the experiment itself, you start to see the same behavior. That indeed this is the reference. So ITO here and gold here. And then when you change the ITO for IOH, you increase the near-infrared transmission. So the CQE response here goes up. And then when you replace this gold layer for ITO, this part also improves, right? And as a result, in the current between the two cells, so the wide bandgap and the narrow bandgap, you are starting from a mismatch, and then quite soon you're actually have a mismatch in the other direction. So now your wide bandgap is a limiting subcell, and then when you go a step further, the mismatch gets even worse. But you can improve it afterwards by working more on the wide bandgap side. So finally, we do that by changing the bandgap of the wide bandgap cell, because there's not much else that you can do. So we narrow it a little bit, going from 1.80 to 1.77 EV. That shifts the bandgap a little bit to the red, and we try to do the same thing again. That we and this is the IVs of the two single junction cells. We replace the ITO for IOH, and you get again this increase in the near-infrared response. And then when you replace the gold for the ITO, you get a very good current matching between the two cells, so between 16.3, 16.5. And that is being done with a 600 nanometer narrow bandgap cell, which is quite difficult using just a regular tandem stack. But there are some challenges still. So for instance, the first one is the voltage. So the moment, for example, you go from the ITO front electrode to the IOH front electrode, so from this red to this orangish one, you incur a voltage loss. And we're not entirely sure why that is, because energetically, as much as you can measure with UPS, everything seems to be the same. But still you do, and we do that consistently. But in this case, at least, the loss in the voltage is more than compensated by the gain in the current, right? So as a result, your overall device performance efficiency goes up. But the moment you change this gold layer for the ITO, and that's to go to the blue one, you improve the current for sure, but you now lose a bit more voltage, and that we think has to do with the conductivity of the ITO layer compared to the gold. And in this case, the current improvement does not really improve the overall performance of the cell. So optically, this would be most favorable, but if you take everything together, this one kind of works the best for us. So at the end, we can get a 23.1% tandem solar cell with it, and you can scale this up as well to a square centimeter. Yeah, so that brings me to more or less the end. So in terms of a take-home message, I hope that I've convinced you that it takes two to tandem, and By that I mean the two subcells, they need to kind of work in a very good partnership. The focus of the field in the last few, like in the beginning of this area, was to optimize the perovskite, but now I think it's changing more towards how to kind of build a partnership between the two cells, and that is very important for efficient tandem device. And to do that, we looked at how to tune the band gap, which is quite straightforward. How to do charge selective contacts and interfaces, so self-assembled monolayers, interfacial passivation. In the integration end here, we looked at the role of this interconnection layer, so the nickel oxide in the case of the perovskite-silicon tandem, and the tin oxide in the case of the perovskite-perovskite tandem. And then finally, light management to achieve current matching between the two cells, and which is almost critical at this point to get a high efficiency device. And the same principle in holds when you want to make a triple junction solar cell, or you want to go further. And there is the band gap tuning that is, I think, the primary challenge, because you would need a 1.9 or 2 EV perovskite solar cell, which is not very easy to make efficient and not very easy to make stable. So the materials challenge is quite large there, but it's also a very good opportunity for research. We observed that the perovskite HDL interface and the perovskite C60 interface are kind of the sites for primarily a lot of voltage loss. So we optimize it by using SAMs in the case of the HDL, and by using a covalent chloride passivation layer in case of the ETL. But here there's a challenge in my mind, at least, that these SAMs have showed up a few years ago, and now the library is growing. But there are some let's say design considerations, like it needs to be a carbazole, it needs to have a phosphonic acid linker, but I don't think there's as much work on or understanding, at least, on how these SAMs organize, how they kind of interact with each other, and how they depend on the substrate that they're being deposited on. And I think one key SAM that is being focused on right now, there's been a few papers at least in the last 2 or 3 weeks, is this methyl 4-pack SAM, which is a nightmare to spin coat on because of the de-wetting. But recently there are some groups which have figured out ways to have better wetting on these on this layer. So there is still quite some work on that front, which is quite interesting. Then in terms of the current mismatch, which is a key component of my talk today, we see that there's a mismatch because our absorbers are either too thin, or we have parasitic absorption in the interfacial and charge transport layers. We have optical interference, which reduces primarily the response in the near infrared. And we overcome it by tuning the band gap, by changing the absorber layer thickness that you can do, by working with more transparent charge transport layers. So, for example, the SAMs. And in the case of the perovskite tandems, most importantly for us was the use of very transparent electrode layers and interlayers. And the nice thing is that all of this can be you can start off on this area with optical simulation, so you don't have to go to the lab directly. But so the optical simulations are a very good guide for what you can do afterwards, right? And out of all of these, I think the most important two, in my opinion, where we can still change materials and tune them, is these TCO layers, which have changed in the case of the perovskite silicon tandems quite dramatically in the last few years, but still kind of in the beginning for the perovskite tandems. So we're still using ITO in most of the reported work, but as we show, it can go much further. And the transport layers of SAMs have come in, but I'm sure there's more to explore there. Okay, and with that, yeah, I would like to thank you for attending, and please feel free to ask any questions.